So as you can see, we have seen in the previous classes, right, with regards to the receiver, where it had a preamplifier, a mixer, and then an amplifier. Then this goes to actually a demultiplexer. So this section is what we are going to discuss today in our class. Okay, yeah. So the input demultiplexer separates the broadband input covering the frequency range 3.7 to 4.2. So that's what we had. The range which is from 3.7 gigahertz to about 4.2 gigahertz. And we will just refer to the figure here, okay, the previous figure, which actually mentioned, about these ranges. So I will just show you, yeah. So I will just show you these ranges is what we are talking about. So this will go into a demultiplexer, okay, and there are a lot of frequency divisions that happens. As I told you, there is about 40, considering your guard band as well as your uh, the timing for your data, okay, the communication signal. So combining both, we will have about 40, and that is going to go to your mux, and one of them is going to pass as your output. Okay, so that is what we refer to the figure, and the separate channels which are labeled 1 to 12 are shown in detail. So these separate channels, okay, that we have seen 1 to 12 are actually shown here. So here what we are trying to do is, just a moment. Okay, so you can see that here it has been divided into odd and even numbers, okay, the 12 transponders. So 1, 3, 5, 7, 9, and 11 are picked up here, okay, in the first half, and in the second half you can see that the even numbers 2, 4, 6, 8, 10, and 12 are picked up, right? The channels are usually arranged in even numbered and odd numbered groups. This provides greater frequency separation between adjacent channels in a group. So by doing this, we can have greater separation between the frequency. So what is this greater separation? Which means I can gain few frequency between each band. Adjacent channels in a group, which reduces adjacent channel interference. So we are already using guard band. Okay, so along with guard band, if we are able to separate them in the form of odd and even, as shown here, okay, so that is going to help us in getting uh, less interference. Okay, so it's going to work out more with the interference. So it's going to help us have a distortion-free signal. So here I will be using a coupler. Okay, just a moment. Okay, so that we have separated the odd and even, okay, just to make sure that we have frequency gain. So here, you can see that you have a 3 dB coupler, which is actually used to, you know, in order to separate them. Then I have matched termination at the end. Fine. So this is one of the examples for your input demultiplexer, which is actually taken up from a handbook, uh, and it's a draft of 1984. Okay. So from the output of receiver, this is fed to a power splitter, okay, which in turn feeds to two separate chains of circulators. Okay, so this is what you see, which is actually connected, okay, to the block. The full broadband signal is transmitted along each chain, and channelizing is achieved by means of channel filters connected to each circulator. Okay, so it is connected to each circulator here. The channel numbers correspond to those shown in the previous figure. Each filter has a bandwidth of about 36. So we have seen this, right? 36, and is tuned to appropriate center frequency. Okay. And although these are considerable losses in demultiplexer, they are easily made up in the overall gain for the transponder channels. So these are made up in such a way that it is able to take up a bandwidth of about 36, and due to this odd even concept, okay, we can even have a better noise cancellation. Okay, so next, talking about the power amplifier. A separate power amplifier provides output power for each transponder channel. Okay. So you can see that here for each channel we have a separate. This is a filter, okay, band pass filter, and then it passes. For each transponder channel, as shown in the figure, each power amplifier is preceded by an input attenuator. Okay. So before we get into the explanation, okay, just look at these diagrams here, where you have at 0 dB here, then this will be a minus 1.5, then this is 60, 50, 48, 104, and 102 dB. So what is happening here? This is nothing but the first one is your filter, okay, that you can see here. So I have received a signal. This is my antenna. Okay, received a signal. So this is my filter, band pass filter. Then it connects to my receiver. Okay, both are receivers. As I told you, there is a copy of these devices on the upper half, and at the lower half there's a copy. And then it gets into your 3 dB coupler that we saw previously. Then this 4 is your demux. So this is the 3 dB coupler. Okay, and here is what we are talking about. Just a moment. Fine. Okay, so it has each power amplifier, okay, is actually having we have a 3 dB coupler here. Then it gets into your demux. Okay, so once it gets into your demux, then the next thing is your attenuator. Okay, so attenuator, normally we have a variable resistor here. Okay, and it gets into your amplifier. Okay, this section is your amplifier, and then it gets into your mux. Okay, multiple inputs and single output, and this will be your antenna, which actually transmits the signal. So this will be receiving the signal, and this will be transmitting the signal. So ultimately, we can see that your typical diagram, okay, of the relative levels in a transponder. So inside your transponder, all these are actually present, right? This is necessary to permit the input drive to each power amplifier to be adjusted to desired level. The attenuator has a fixed section and a variable section. So, this that you see here is a variable section. Okay, that's your attenuator. The variable attenuation is needed to set the level as required for different types of service. Okay, so an example is nothing but the requirement for input power back off, which is discussed later. So we will be seeing this, okay, power back off, and we will see this in the next upcoming classes as to how power back off is actually considered. Okay. Because this variable attenuator adjustment is an optional or operational requirement, it must be under the control of CT&C. Okay, so this attenuators, okay, we will have control of these attenuators in the ground station. Ground station is nothing but your TT&C, which is telemetry, tracking, and control. Next, we have something called traveling wave tube amplifiers. So this is just like the electron gun that you can see, okay, traveling wave tube and the various supplies. Okay. So typically you'll have to understand as to once there is a potential here, okay, you will have a heater coil, then you have a cathode, okay, and through this actually the electrons pass through. You have anode, then you have magnets, then you have attenuators. So these attenuators will actually narrow the it will make sure that your electrons are moving in a straight line. Then you have your output line, collector 2. Okay, so here you can see that it is spreaded, and here it will still be narrow, right? And this is in the form of your collector currents, okay, IC, and the potentials across your collectors, EC1 and EC2. So we will be using different semiconductors here, okay, for its operation. So we'll just look into it as to how it functions. In TWT, an electron beam gun. Okay, so this is in short also called as your E-gun or electron gun. It's an assembly consisting of a heater, cathode, and focusing electrodes. It's used to form an electron beam. So it's a fine beam, just like a laser beam. It can actually activate these electrons and it passes from one end to the other. A magnetic field is required to confine the beam to travel along inside the wire. Okay. So this magnets that you see will actually try to change the path of your electron. So those electrons which are getting generated from this point will actually be moving inside, and because of these magnets, we will just see that these electrons can be made sure to be in a straight line of sight. For high power tubes, such as might be used in ground stations, the magnetic field can be provided by means of a solenoid and DC power. Okay, so that is what that you can see here, where actually you can look into the diagram, okay, and how these electrons are confined with these spaces, a small narrow space, using magnets. The comparatively large size of high power consumption of solenoids make them unsuitable for satellites. Now, why do you think so? Why do you think so? It's not suitable for satellites which consumes high power. Can someone unmute and respond? Why is it so? Students, let there be some communication, okay? Let us not have a single-sided communication. The batteries that are available on the satellite will have to sustain during this eclipse, okay? So if in case I try to have these high power consuming circuits, then during eclipse, as you all know that few eclipses can last to up to 72 to 75 minutes, right? So don't you think these high power consuming circuits will actually drain off the battery, and we will lose contact with our satellite, right? So that's the main reason as to why we do not prefer having high power consuming circuits. Instead, we go with something which takes less power. Okay, so that even when it's operating in battery, the battery doesn't get drained off, and the battery still remains. It gets back its solar energy using the solar cells, and then the battery gets recharged. So there is no miss, there is no link getting missed if in case I'm using a low power circuits. Is that clear? Have I made myself clear?
Yes, sir. Yes, sir. Yes, sir.
Yeah. Okay. So we require circuits which are low power consuming, okay, so that we do not want it to get into graveyard. Fine. So the RF signal to be amplified is coupled into the helix at the end. Okay, so that is what you see here, the helix. Okay, so this is like a spring. Okay, the input power and the output power. It's like a spring. So it is at the nearest cathode and sets up a traveling wave along the helix. So as this wave passes through, it makes sure that it is actually passing through this wire, okay, which is coiled like a spring. The electric field of the wave will have a component along the axis of the helix. So you have an electric component uh, because I'm giving an input power here, and I will make sure that these electrons are actually moving along only this path. In some regions, this field will deaccelerate the electrons in the beam, and in others, it will accelerate. Okay. So the movement of your electrons are actually impacted by this helix and the magnetic field that you see. Okay. So the average beam velocity, which is determined by your DC potential on the tube collector, is slightly greater than the phase velocity. Okay, so you can see here there's an impact with the power with your spring. Okay, this helix, and there is also an impact from the magnets. So due to which these electrons can be deflected along its path. Okay, so we have to make sure that there is a proper balance between the magnets and the power that we are giving. So if there is a proper balance, then we can make sure that these electrons can pass through in a straight path. So if there are no straight paths, then electrons can actually collide with each other, and there is a loss of energy. So if they are loss of energy, they will move down below the Fermi level and consequently lose its energy, and there wouldn't be any energy band for that electron. Okay. So the average beam velocity is determined by the DC potential. Okay, so how much ever potential that you are giving, so accordingly it starts functioning. Okay, so you can see that there is a DC potential at every point, at the initial point, then here at the grid, okay, then here for the anodes. Okay, so you can see that there's a DC potential everywhere, so you have them in control. Under these conditions, an energy transfer takes place. The kinetic energy in the beam, kinetic energy is the energy which is actually when in movement, okay, when in movement. In the beam being converted to potential energy in the wave. The wave actually will travel around the helix path at close to the speed of light. So that is the speed. Okay, that's the speed of the wave. So it's actually almost close to the speed of light, but it is the axial component of the wave velocity which interacts with the electron beam. So it is dependent on the magnets, it is dependent on the helix, the potential differences that we give, the voltages. Okay, this component is less than the velocity of light, approximately in the ratio of helix pitch to circumference. Because of this effective reduction in phase velocity, the helix is referred to as slow wave structure. Okay. So this helix that you see is called a slow wave structure. Why is it called a slow wave structure? Because it is not able to catch up with the speed of light. The advantage of TWT over other tubes, other types of tube amplifiers is that it can provide amplification over a wide bandwidth. Okay, so it has a range of spectrum. So once we have a range of spectrum, then it's easy for us to pick up signals and work on them. Input levels to the TWT, okay, this is traveling wave tube, must be carefully controlled. Okay, so whatever levels that we are having here, the inputs should be carefully calibrated. So which means whatever voltages that you are giving here at the initial point and here, all these voltages are connected to each other. If there is a slight increase or decrease, then there's a possibility of you losing this electron beam. Okay, so it becomes very sensitive. The electrons becomes very sensitive. So we should control them properly so that we can minimize distortions. The worst of these result from non-linear transfer characteristic of the TWT. So this is your transfer characteristic. At one point you can see, at one axis you can see the power, input power, and at the other axis you can see your output power. Okay, so it will actually lose its linearity. You can see that it will lose its linearity and it will slightly get into saturation point. So when it gets into saturation point, that's when your electron beam loses its destination. Okay, yeah. So power transfer characteristics of the TWT. The saturation point is used as 0 dB reference, both for input and output. Okay. So it will be, the electrons are energized till here, and once, as it proceeds, it probably gets into something called a saturation point. Okay. So at low input powers, the output input power relationship is linear. So whenever my input powers are lower, okay, so at lower power levels, these are going to be in the linear form. As the power increases, as my input power increases, this linearity is lost. It will, you can actually see that the wave is having a slight change from its linearity property. Okay, at higher power inputs, the output power saturates, and the point of maximum power being known as saturation point. So this point is convenient reference point, and input and output quantities are usually referred to it. Okay. And during the linear region, okay, we take 1 dB as our reference, and this is the point where your actual transfer, okay, the transfer curve that you can see in the figure that we saw previously, okay, is going to be linear, and then after this point, after this compression point, you can see that the linearity is lost. Since phase delay is directly proportional to time delay, this results in a phase shift which varies with input level. So here, this input level, this input power that we see, okay, there's a fine balance that needs to happen between input power and the output power. Okay, so whenever there is a fine balance between them, okay, so that's when we can make sure that this is actually in the form of linear. Okay. Denoting the phase shift of saturation by theta s, and in general by the phase difference relative to theta minus theta, as this is plotted in the figure. So you can see that, okay, there is a phase shift at one end and there is power in, okay, the input power at the other end. So this is the same graph that we see, and you know, you can see that this is actually with reference to degrees per decibel, how much change it's happening, and we will be using this for our AM and PM conversion. Okay, fine. So this is plotted. Thus, if the input signal power level changes, the phase modulation will also result. So this is nothing but your amplitude modulation and your phase modulation. So what is phase modulation? It changes. If it's going from 0 to 1, then directly, you know, the shape of the wave is actually changed. Okay, fine. The slope of the phase shift characteristic gives the phase modulation coefficient in degrees per decibel. Yeah, so that is what we saw here, degrees per decibel. The curve of the slope is a function of input power. So you have input power, you have phase shift. Okay. Fine. So frequency modulation is usually employed in analog satellite communications. So we have seen frequency modulation. How is frequency modulation, students? Can you tell me what is FM? How are the signals same in FM? Okay, so your frequency modulated signals are in such a way that whenever the amplitude of your message signal goes high, the frequency is increased, right? So the frequency is varied and amplitude and phase are kept constant, right? Okay. So however, unwanted amplitude modulation can occur from filtering which takes place prior to TWT input. The AM process converts unwanted amplitude modulation to phase modulation. So whichever amplitudes are having spikes, you know, that can change. So this appears as noise as FM carrier because there is a change in amplitude. Okay, where only a single carrier is present, it may be passed through a hard limiter before being amplified in TWT. So we will just look this diagram here. Okay, yeah. So where you can see that, you know, there is a lot of things, you know, that takes place between the cathode, okay, the the grid section and the collector section. There are a lot of things that happens in between, modulations that happens. Okay, where only a single carrier is present, it may be passed and through a hard limiter before being amplified in the TWT. Okay. The hard limiter, what's a hard limiter? It's a circuit which clips the carrier amplitude close to zero baseline to remove any amplitude modulation. Why do we need to remove any amplitude modulation? Because that is actually coming as a noise in our FM carrier. Okay. So the FM is preserved in zero crossover points and it is not affected by the limiting because the frequency is impacted, not the amplitude for an FM signal. The TWT also may be called on to amplify two or more carriers simultaneously. Okay, so what is happening here? We can make sure that this TWT may be called to amplify. So we can use this as a low power circuit as an amplifier. Okay. So this can be referred to as multi-carrier operation. So TWT, which can amplify two or more signals, and hence it is referred to as multi-carrier operation because it can deal with many carriers, more than one carriers. Now the amplitude modulation and phase modulation conversion is then a complicated function of carrier amplitudes, but in addition, the non-linear transfer characteristics introduces more serious form of distortion known as intermodulation distortion. Now what is happening here? We are using a lot of modulation techniques here. AM is there, PM is there, then we want FM. So because of this, there can be another noise that gets created, which is nothing but called your intermodulation distortion. So these can be expressed in the form of Taylor series. In your mathematics, you would have looked into these series. So as I was mentioning, you can refer to this, okay, with or you can express with the help of a Taylor series. The intermodulation products fall on the neighboring carrier frequencies. So because of which, you can see that we are looking into something called input backoff. Input backoff, output backoff. I will explain this, and it's a very important concept. Similar intermodulation products will arise from other carrier pairs, and when the carriers are modulated, the intermodulation distortion appears. Okay, so why is this intermodulation? Because we are referring to many modulation techniques, AM, PM, FM. Okay, so we will have a distortion. Appears as noise across the transponder frequency band. So it appears as a form of noise. So noise is normally not needed when we are communicating from one point to another. In order to reduce the intermodulation distortion, the operating point of TWT must be shifted closer to the linear portion of the curve. Okay, so here you can see that from the point of non-linearity, I will make sure that I will decrease my input, okay, because I have control of my input power. So I will decrease my input and make sure that it just stays in this line. It just stays in a linear line. So if I increase the input, then only, it's actually getting into your saturated point. So if I decrease the input, then it will remain in my linear point. So that is nothing but called your input backoff. And the corresponding output is called output backoff. Okay. So in order to reduce the intermodulation distortion, the point must be shifted closer to the linear curve. The reduction in input power is referred to as input backoff. So this is an important concept which will be asked many times in your examinations. Okay, what is meant by input backoff? What is meant by output backoff? Explain this concept with the help of a graph. So when multiple carriers are present, the power output around saturation for any one carrier is less than that achieved with single carrier operation. So when there are more carriers, more than one, okay, the output power for any one carrier is less than that achieved with a single carrier. So using a single carrier option is always good than having a multiple carrier. Okay, because you will have to deal with even those graphs as well. Okay, so this will be our last slide for today's session. When multiple carriers are present, the power output around saturation for any one carrier is less than that achieved. So we have seen that. Okay. The input backoff is the difference in decibels between the carrier input at the operating point and the saturation input, which would be required for single carrier operation. So single carriers are always advisable than to have multiple carriers. The output backoff is the corresponding drop in the output power. Okay, so if you can see the graph, so there is a slight backoff that is happening with respect to output. Okay. Backoff values are always stated in decibels relative to the saturation point. So this is my saturation point. So relative to that only, I'm going to consider. See here also, it is in the form almost an, there is a, you can see that it is not stable. Okay, slightly it is exponential. But at this point, okay, from this point is where it will start becoming constant line. So this point is considered as my saturation point and the point from which the deviation of linearity starts. Okay, so these 2 points are considered, and I will make sure that my input levels are reduced so that it comes in the linear graph. Okay, fine. As a rule of thumb, output backoff is approximately about 5 dB less than input backoff. So why is the need? The need to incorporate backoff significantly reduces channel capacity of satellite link because reduced noise ratio, okay, CNR, carrier to noise ratio, and that's going to help us in communicating properly if the electron beams are maintained. Okay, so in the upcoming classes we will look into the antenna subsystem, okay, the formulas involved and few diagrams that are needed for our understanding. Okay, thank you.